Hello, everyone. My name is Krishna, and I'm working with Eric and Qingqing. And the title of our project is Using Machine Learning Models to Predict the Spread of COVID-19. For the contents of this presentation, we will first introduce you to our project. We'll give you a brief overview, and then we will talk about some model requirements. And then we will talk about three different models, the three different models used, a curve fitting model, SVM, and a hybrid neural network model. And at the end, we will compare all of the models and give you a conclusion.
Hi. So this project involves predicting the number of cases for COVID-19 that will happen in the next few weeks, just using data that's currently available. Predictive models for COVID-19 have been developed using all sorts of different predictive models and mathematical models, and our models will specifically use machine learning techniques in order to analyze the number of cases every day and predict the future number of cases. We also predict deaths with deaths with our models, and we can predict up to 4 weeks in advance. The three models that we'll be using are curve fitting, specifically the ARIMA regression model, support vector machine, in particular support vector regression, and a hybrid neural network. COVID-19 prediction is very useful for many people, including health officials, policymakers, school boards, and just average people wanting to know whether they should prepare to self-quarantine. We decided that so that our models could be compared fairly, we would all follow the same format regarding what data we would use to make the prediction. We used the COVID-19 cases and deaths data from the site ourworldindata.org, and we used the data. We used the data from January 27th to October 25th to train our models. To test our models, we predict the number of cases and the number of deaths for 7 days, 14 days, and 28 days after October 25th. And we use the mean absolute error when validating against the actual cases. Those average error rates are how we grade our models to determine how good they are.
All right, so we can start with the first model, which is the curve fitting model. Now, we're gonna begin by talking about the data processing method. As Eric already mentioned, we used two different data sets, one to predict the number of daily cases and the other one to predict the daily deaths. The range of dates is from the 27th of January to the 25th of October. The way the curve fitting method processes the data is that it splits it into training and validating sets. The training data set consists of all of the cases from that same range of dates, but the validating set consists of the number of cases after the 25th plus 7 days, 14 days, or 28 days, depending on how many cases you're forecasting. And as you can see on the figure on the right, that is the data of all the newly or the daily cases. For the model construction, this model requires to have stationary data. Stationary data is one that has a constant mean and variance. To check if the data is stationary, we can perform test statistics on it. The test statistic or the test that we use is the Dickey-Fuller test. What this does is that it calculates the test statistic of the data, and if it is smaller than the critical values, we can say that the data is stationary enough. When the data is not stationary, we can make it stationary by either using two different methods, by differencing or decomposing. We use differencing in this curve fitting model, so I will be talking about that, but Qingqing uses decomposing and she can talk about that method. What this does is that we can remove the trend and seasonality in the series. We need this because we use the ARIMA model, and this model requires a stationary data. According on the data set that we use, we can see if we need to transform it or not. And then after fitting the model, we can then convert everything back to the original scale, and get our final results. Now here on the left, that is the data set for the new cases. And then we try to transform the data set. We do a log transform. The plot on the left is where we apply the, where we do the test statistics. We can see that we don't have a constant mean or variance. We're plotting the standard deviation here because it's easier to see. But then we have to transform it. And so that's the plot, the figure that you see on the right. So since we have to make our data stationary, as I said, we apply differencing, the differencing method. The test statistic before we did differencing was of 1.7057. And as you can see in the middle, all the critical values, it's larger than all the critical values. That's why we had to transform it and apply the differencing method. And the test statistic after doing this is of -5.30, which is smaller than all the critical values. We do this by smoothing, which is just taking the rolling averages, and then the figure on the right shows you a more stationary data with a more constant mean and standard deviation. So once we have the stationary data, we can now use fit the ARIMA model. This stands for autoregressive integrated moving averages. This model is essentially just three different models, and it's an AR model, MA, and then the combined versions of the two of them. And so this model requires three different parameters: your P, which is the number of autoregressive terms, your D, the number of differences, which would be 1 here because we use for the differencing method that we use, we did it once. So Then you have your Q, which is the number of moving average terms. And then we fit all three different models. And at the end, we compute the RSS and we pick the one with the smallest value. And that's when you know which one fits better. Here you can see all the figures of all three different models. The AR model gives you an RSS of 2.4138. The MA model gives you an RSS of 2.2665. And the combined model of both AR and MA gives you an RSS of 1.5253. The RSS is used to measure the amount of variance in a data set. So as I said, we pick the one with the smallest one, and so we pick the combined model. Here we have a plot of our predictions. The original data is in blue and the fitted values is the orange. It's not perfect, but it's pretty decent. And now we did do a forecast of 7, 14, and 28 days, but we chose to show you the 28-day forecast because it still contains the 7 and 14-day forecast. And so here you can see the original data, and this is already converted back to the original scale. So in blue is the original data, and in orange is the predicted data, and we get an MAE of 27,581. Now we do the same thing for the new deaths data set. So we have to analyze it first. But if you can see the original data here in pink, purplish, we get a test statistic while checking for stationarity. The first test statistic we get is of negative 3.59, which compared to the critical values is smaller than them. So this is already stationary enough to be used as is without having to transform or do any differencing or decomposing. And then we do the same thing. We apply the ARIMA models and we look at the RSS values as well. And we take the smallest one. And again, it's the one for the combined model, which is of 10.1338. And here we have the figure for a 28-day forecast. And we get an MAE of 2,935.
So our second model was a support vector machine, or SVM for short. SVM is a type of model where you can imagine the data points as being plotted in some multidimensional space, and basically we're trying to find a linear correlation that describes the plot. And the special way that we do that in an SVM is we bound the points up and above by certain hyperplanes, which represent our upper and lower bounds on our linear function. And we try to make it so that the distance from the hyperplanes to the distance from we try to make it so that well, let me see. We try to make it so that the distance from our hyperplanes to the data, or the deviation of our data from the hyperplanes is the least. And so anyway, So anyway, for our SVM model, we used support vector regression, which is a specific type of support vector machine where instead of classifying the data into two distinct groups, we predict a range of values, a continuous variable. So we used the data set new cases.csv and new deaths.csv, just as we did for our other models. For both models, our first step was processing the data to combine the number of cases for each consecutive week of data, because if you see in some of those graphs, the actual number of cases has a predictable cycle for every day of the week. So in order to smooth out and hopefully linearize the data, we collected all of the data for each week into a single training instance. So this model is unique in predicting the data a certain number of weeks in advance rather than a certain number of days. Then before we processed further, we took the logarithm of each case, the number of each number of cases for each week. So our model started with a number of cases for each week for the entire world and also for each individual country. Now we have the logarithm of the number of new cases for each week for those areas. And for my descriptive features, I knew that COVID-19 cases were caused by previous cases, so I figured that good predictive features would just be the number of cases in various predictor regions across the globe in previous weeks, because some countries got the virus ahead of other countries. So as we mentioned, support vector regression was used. In support vector regression, you plot all of the predictive features as well as the target feature in a multi-dimensional graph, and then you try to find hyperplanes above and below the graph that that act as two different approximations of your linear function, and you try to minimize the distance between the upper and lower bounds so you get the best approximation. We chose 5 countries on which COVID-19 had a significant impact, and well, we started with 10 and then we chose 5 with the highest correlation coefficient. We also, for our predictive feature, we also tried correlating the data from each country a certain number of weeks ago with the data we were currently predicting in our training data. So we tried finding the correlation coefficient of the cases in various countries 1 week, 2 weeks, 3 weeks, and 4 weeks ago, and 5 compared to the cases for the world right now. And then we chose the number of weeks ago that gave the highest correlation coefficient between those two variables. We also added the number of cases worldwide from the previous week as a descriptive feature. This just made our model more direct, and it made it so that it hopefully wouldn't perform worse than just predicting the previous number of cases again. So the first model was trained on data from the previous week, so it could only predict when being tested, it could only predict the number of cases up to 1 week in advance. We had to retrain the model using using data from at most 2 weeks ago and at most 3 weeks ago and 4 weeks in order to predict data 2 weeks, 3 weeks, and 4 weeks in advance. So we ended up with 4 models, and out of the 39 training instances for the 39 weeks from, out of the 39 initial data points for the 39 weeks from January 27th to October 25th, we were, for our first model, we were using data up to 5 weeks, before the actual number of cases we were predicting. So we ended up with 34 data instances. And in the other 3 models, we had 33, 32, and 31 instances. For each model, we chose 25 of these instances for our training data, and the others were our validation as we tried to adjust the model. So to test our model, we needed to predict the number of cases for the first 28 days following October 25th. We fed the data from October 25th into our model, into each of our 4 models, in order to get values for the number of cases in 1 week, 2 weeks, 3 weeks, and 4 weeks. Now those were the number of cases for the entire week. So to predict the number of cases for a single day, we simply divided these numbers by 7. Thus, the 7 days for every week all got the same prediction value. Here are the results for the number of new cases predicted per week. To predict the number of new deaths, the exact same technique was used, involving correlating the data with itself and finding the best predictor countries. And for the number of deaths, these were the values that we predicted for the 4 weeks following October 25th. Here's the graph of the actual cases for the 28 days on which we tested our model versus the predicted cases. And here's the graph of the actual deaths versus our predicted deaths.
Okay, all right. Besides curve fitting and SVM model, we also use deep learning to predict the spread of COVID-19. Here I use hybrid neural network. So before talking about the neural network, let's first see the data processing. Next slide, please. Yeah, as we know, COVID-19 recorded the daily confirmed and death cases. So it's the time series data. Usually the time series data will have 2 different components, the systematic and unsystematic. Systematic component usually has consistent or recurrence data that can be modeled very easily, and the unsystematic data components cannot be modeled directly. So in order to extract the systematic component from the COVID-19 data set, we use seasonal decomposition. The seasonal decomposition will decompose the time series data into 4 components. There's the level, trend, seasonality, and noise. Never indicates the average value in the series, and trend shows the increasing or decreasing value in the time series. And third is seasonality, which is a repeating short time circle in the series. And the last is the noise. It is a random variation in the time series. In the network model, I use a Python seasonal decompose. It has two parameters. The period shows how long the short time circle will continue, and the model indicates how all the components will combine into the time series. So there are multiplicative model and the additive model. And in my experiment, I use a multiplicative model with period 7 as a seasonal for the seasonal decomposition. And the trend after the decomposition is used as a data set to train the model. Here, I will show why I choose a multiplicative model and the period 7. And this figure shows the component after the seasonal decomposition. I can see the trend is smooth, and the seasonal is simple enough, and the residential is fairly plain. So we also do some other seasonal decomposition, but they're not very good. In the next slide, I show the additive model with period 7 for the seasonal decomposition. Here we can see the residential has very good, very large value. And then in the next slide, I use the multiplicative model with period 15. And we can see here the seasonality is not simple enough, and also there's still some circle repeat in the residential. So that's why I use a multiplicative model with period 7 for my experiment. And after the decomposition, we got the trend. And then the trend was split into the segment with window sliding with a window length 7 and step 1. For each segment, it represents by the xi. So I means the I segment for the data set. Xi contains 7 consecutive data to stand off a period, and the day the next day of the xi are used as a label of the segment. So both the xi and yi construct a symbol for the input of the neural network, and then the Python normalization was used to normalize the data sets. Now we have the data set ready, so let's move on the model construction. The hybrid neural network is inspired by the stock trained prediction mode. The multiple time scale feature is used in the hybrid neural network to learn and predict the spread of COVID-19. And the structure of the model is displayed on the right figure. And firstly, the 2 layers of the convolution neural network is used as the feature extractor to extract 2 types of features. They are the F2 and F3. And with the Rowley data cases at S1, there has 3 times schedule features, and each of them reflects the relatively short, medium, and long-term features in the COVID-19 data set. And then consider the time dependency existing in the different features. The proposed hybrid network use 3 long short-term memory recurrent neural networks to capture such dependency respectively. And finally, 2 fully connected layers are used to learn the joint representation for predicting the confirmed cases and death cases. So after the neural network we got the predict trend. Here is a figure shows that the predict trend fits the real trend very well, and the average error is about 5,000. But this is predict is for the trend. Since we use seasonal decomposition, so we need to compose the original components to do the forecasting of the COVID-19. So next slide. We use the multiplicative model to compose the predict trend with the seasonality as the residential. For the residential, the mean of decomposition is used, and also the 95% confidence interval of the residential are used to draw the high and low boundaries for forecasting the COVID-19 data. And this figure shows the real cases and the forecasting cases after the composition. And the red and green are the high and low boundary to indicate that our predicting COVID-19 cases will exactly falls between those two boundaries. And in order to validate our neural net model, we use a 4 weeks data to validate the models. And this figure shows a validation for 4 weeks of daily conformal cases all over the world. And the mean absolute value are calculated here is about 33,000. And then the same process the same experiment are done for the daily death cases all over the world, and we got the validation of 4 weeks for the death cases, and we can see the figure. The trend fits very well, and the mean absolute error is also fairly low. It's about 800. And well, as the previous two models, the 1 week ahead and 2 week ahead and 4 week ahead mean absolute error also calculated, and they will be showing on the the model comparison part. So that's all for the neural network part, and I will switch to Eric. Eric, it's your turn.
So after we constructed our 3 models, we compared them all. We compared them all to see which one gave the most accurate prediction for the number of COVID-19 cases and deaths within the range that we were testing them. We used the mean absolute error, which means for each day within the range of 28 days, we found the actual number of cases minus our predicted number of cases, and we just that was like we just took the absolute value of that for our error, and then our mean absolute error was just the average of all of those values. So we can see that the curve fitting model gave the lowest errors when we were predicting the number of cases, and the hybrid neural network gave the lowest number of errors when we were predicting the number of deaths. In conclusion, of all our 3 models, the 2 models the two models, the curve-fitting model and the hybrid network model, the two models that had to do with time series gave the best correlation to the output. So they gave the most accurate predictions of the number of COVID-19 cases and deaths. It's not surprising that these were the two models that had something to do with time series analysis. After all, COVID-19 data is an actual time series because the number of cases per day is, it's a statistic that varies with time. So all that seasonal decomposition and variance and splitting the data into different components that varied over different periods of time was probably the key to creating an accurate model. In the future, we could refine these models by adding in other factors, such as government response to the pandemic, the weather and climate data for the various countries, and the country's economy, not to mention things like public opinion on the virus. Is that a... So here are the references we used. For time series, an introduction to support vector regression, and more time series. Thank you. Thank you for listening to this presentation. I hope you enjoyed it. If there are any questions, feel free to ask them. I'd like to thank Krishna and Qingqing for being my partners, and I'd like to thank New Mexico Tech and Professor Jun Zhang for giving me the opportunity to present this research.